Welcome back. We're continuing 8.3 with example 3, applying an exponential decay function. So in this example, we're given, it says, in a sample originally having 1 gram of radium-226, the amount of radium-226 present after t years is given by, and they gave us a formula. It says A of t is equal to 1/2, which means half-life, raised to the t over 1,620, which represents the years, where A is the amount of radium in grams and t is the time in years. So A says, how much radium-226 will be present after 1,620 years? So first thing, you're going to write your equation. It says A of t equals 1/2 t over 1620. That is a generic equation they gave us. This will be used repeatedly for the next 3 parts. So they want to know it's present after this amount, 1,620 years. So the t value is being replaced with 1620. So when you go to your equation, I'm writing 1620 in the parentheses because that's what t is being replaced with. So 1/2 to the 1620 divided by 1620. Well, 1620 divided by 1620, that's about value of 1. So I get a half. But what does the half mean? Remember, we started out with 1 gram of radium. We now have 1/2 gram of radium. So in 1,620 years, we've done a half-life. We've halved the amount of weight that we started out with. So now we're going to find, B says they want us to find how much radium-226 will be present after 3,240 years. So again, our equation, A of t is 1/2 t to the divided by 1,620. And we're replacing the t with now the new value. The t value for this time is going to be 3240 is what we're replacing it with. So we have A of 3,240, 1/2 of 3240 divided by 1620. Well, that numerator value is actually double the bottom value. So we're actually looking at 1/2 power of 2. Well, a half raised to the power of 2 means 1/4. So it means we have 1/4 grams, which is 0.25 grams left of radium. What do you guys think will happen when they want us to find how much radium-226 will be present after 4,860 years? Remember, it's half-lives. The base value here is a half, so it means you're doing a half of the previous value. So in this instance, our t value is now 4,860. So we have our equation, A of t, 1/2 to the t over 1620, which is 1/2 to the 4,860 divided by 1620, which the numerator happens to be triple the denominator. So we're actually looking at 1/2 raised to the 3rd power. That is actually 1/8 grams, which is 0.125 grams left of radium. So exponential functions are often used to model population growth. Suppose the initial value of a population at some time t equal to 0 is p naught, which is our initial value. If the rate of the increase of a population is r, that's represented by r, then after t years, remember t has to be in years, the population p of t is given by, and they give us an equation. P of t is equal to p naught, which was our initial, times the parentheses 1 plus r, which was our rate, closed to a power of t. So in the situation that you will know your initial and you will know your rate. They will give you a time frame as to how you want to use it. So in example 4, it says applying an exponential growth function. It says the population of the Bahamas in 2008 was estimated at 321,000 with an annual increase of 1.39%. So it says find a mathematical model that relates the population of the Bahamas as a function of the number of years since 2008. So we kind of already have a base value of what our mathematical model is going to look like. I am going to use the equation that I wrote out here, our initial. So we know that our mathematical model, P of t, is P naught times 1 plus r raised to the t power. But that's only a generic formula. And this one is saying that the population in 2008 was estimated at 321,000 with an annual increase of 1.39%. So we need to identify specific things. The 321,000 happens to be our P sub 0 or P naught. That is 321,000. Then they tell you our rate. It's an increase of 1.39%. 1.39%. But you're not allowed to use percents because if you think in banking situations, they don't use the percent, they use decimal form. So you need to change this to decimal form so you can either divide by 100 or move the decimal place back 2 places. So I'm 0.0, 2 decimal places, 139. 0.01, because if I multiply by 100, I move over to the right 2. If I divide by 100, I move to the left 2. So this is our R value right here. This is what we're using for R. This is what we're using for P naught. So it wanted us to find an equation that we can use. So P of t stays as is because we don't know how many years. Our initial value was 321,000, so you're going to write 321,000. And in parentheses, you're going to write 1 plus 0.0139 to the t power. You can consolidate this piece right here to finalize your equation as P of t equaling 321,000, 1.0139, because you're just adding the dollar to this, to the t power. This is my mathematical model. Since we found our mathematical model, we can now try to figure out what it says, hypothetically, if the annual rate of increase remained the same, so we're keeping the same rate. Use the model from A, which we came up with, to predict the population of the Bahamas in the year 2025, round to the nearest 1,000. First thing we need to remember, in our original problem, this is the number of years since 2008. So the year 2008 represents t of 0. That's the first thing I need to remember. We need to get to the year 2025. So that is going to be how many years after 2008? Well, if I add 17, I get to 25. So that is 17 years. So then we are going to write our equation. P of, instead of a t, I'm going to write 17 because it's going to be 17 years after the fact. So 321,000, 1.0139 to the 17th power. Okay, so we're going to plug this into a calculator. And remember the rule of thumb, there's parentheses here. So you're going to write 321,000, parentheses of 1.0139, close it, caret 17. So in the calculator, you write 321,000, parentheses, 1.0139, close it, hit the caret key, type 17. So I'm going to bring my calculator over. And we're going to write 321,000, parentheses, 1.039, close it, hit my caret key here, and hit 17 because I want to raise to the 17th power, and then hit equals. It says the population in 2025 should be 615,133. Remember, you don't have 0.4 of a person, you can only have whole people. So I'm going to go with just whatever's to the left of the decimal point. So 615 133. So our population is going to be 133,000 people.